Hello everyone, and welcome back to this video series on anaerobic digestion. We'll continue our discussion about alkalinity and extend it to volatile fatty acids. Reactor volatile fatty acids concentration is one of the most important operational parameters when it comes to anaerobic digestion processes. This is because of the accumulation of volatile fatty acids typically indicates poor methanogenic health, which may be a sign of an impending reactor upset. Moreover, it is vital to understand the concentration of unbuffered volatile fatty acids to estimate the reactor's alkalinity demand. In this video, we'll learn about what these volatile fatty acids are, why they accumulate in the reactors, and common methodologies used for detecting them. So volatile fatty acids are short-chain organic acids having 1 to 6 carbon atoms. These short-chain organic acids include formic, acetic, propionic, butyric, valeric, and caproic acids, and their isomers. These acids are formed as intermediate substrates during an anaerobic digestion process. Their excessive accumulation represents process inefficiency or outright process upsets, since they represent the partially digested substrates left over in the last step of methanogenic activity by methanogenic archaea. As we discussed in earlier videos, biogenic methane formation under anaerobic conditions happens via 3 distinct methanogenic metabolic pathways. The 3 different methanogenic metabolic pathways are shown in the diagram here. A majority of methane is produced by acetoclastic methanogens, which degrade acetic acid and generate methane and carbon dioxide. This pathway represents typically 70% of the methane produced in an anaerobic reactor. A decline in acetoclastic methanogenic activity leads to the excessive accumulation of acetic acid in anaerobic reactors. The second most important group of methanogens is called the hydrogenotrophic methanogens. These methanogens process hydrogen and CO2 to convert these dissolved gases into methane. This group of methanogens is typically responsible for 20 to 30% of the total methane produced by an anaerobic reactor. The hydrogenotrophic methanogens work in a syntrophic relationship with bacteria responsible for degrading propionic and butyric acids. The syntrophic bacteria degrade these acids to generate CO2 and hydrogen gases, and they can do so in an anaerobic environment because the energy provided for such degradation by hydrogenotrophic methanogens. If hydrogenotrophic methanogenesis slows down or stops entirely, such a condition often manifests itself in terms of excessive accumulation of propionic or butyric acid in the reactor. The third group of methanogens is called metallotrophic methanogens, and they typically represent a very small quantity of methane produced in an anaerobic reactor. Volatile fatty acids have pKa values between 4 and 5, and hence they cause buffering between this pH range. This means they can cause a decline in the reactor pH when a sufficient amount of alkalinity is unavailable. As we discussed previously, once the methanogenic activity slows down, the accumulation of these acids increases due to the higher metabolic activity of acid-producing bacteria, even under the upset conditions. It is noteworthy that the higher concentration of protonated VFAs are toxic to methanogens, and since a decline in pH increases the protonated form of VFAs, a decline in the reactor pH increases VFA toxicity. Moreover, their accumulation slows down methanogenesis even further, causing even more accumulation of VFAs and a decline in the reactor pH. Finally, the pH drops to a value between 4 and 5, and these volatile fatty acids cause buffering in this range. Such an upset condition is called reactor souring and is very difficult to recover from. There are several methods used for quantifying volatile fatty acids. Chromatographic methods are used for VFA measurement, and these are the most accurate methods. An HPLC or GC can quantify the volatile fatty acids accurately, as well as speciate the individual concentration of volatile fatty acids. Knowing the species of accumulated VFAs can be used to determine which methanogenic group is impacted by an upset. In our experience, such information has proven very successful in planning the recovery of anaerobic reactors, since the two main groups of methanogens have distinct environmental and nutritional requirements. A solution can be tailored to specifically meet the requirements of the group that is experiencing an upset to accelerate the reactor recovery process. It is common to use stoichiometric methods to quantify volatile fatty acids and alkalinity simultaneously in on-site laboratories. These stoichiometric methods utilize the buffering properties of volatile fatty acids. The VFAs have an equilibrium constant between pH 4 and 5 as shown in the table here. These stoichiometric methods measure all the VFAs together in terms of the amount of acid or base consumed during the titration process to buffer the VFAs. Although such methods are easier to perform, they have a few drawbacks, such as a few non-VFA acids can also buffer between these pH values. Their presence in the water may overestimate the VFAs. Moreover, bicarbonate alkalinity can also interfere with the determination of volatile fatty acids due using stoichiometric methods. Research comparing different stoichiometric methods suitable for VFAs measurement shows that KEP's titration method is easier to perform and it also generates fairly accurate results. The comparison between different stoichiometric methods used in VFA measurements is given in the table shown here. This diagram shows the KEP's method for alkalinity and VFA measurement. In this method, the sample is titrated down to a pH value of 5 using an acid of known concentration. In the second step, the sample is titrated further down to a pH value of 4.3, and in the third and final step, it is titrated down to the pH value of 4. The amount of acid consumed during these steps is used to calculate total alkalinity and volatile fatty acids using the equations as they are shown here. Other commonly used methods for quantifying VFAs include Ripley's method and its other variants, including Fostak method. The diagram here shows the Ripley's ratio method. In this method, the sample is titrated down from its initial pH to the pH of 5.75 using an acid of a known concentration. Further, the sample is titrated down to pH value of 4.3 in the second titration step. Ripley's ratio is calculated by the equation given here. The scientists who proposed this ratio observed that the ratio of 0.3 or less represents a well-buffered anaerobic reactor. It is noteworthy that this ratio only provides the information about the current buffering capacity of the reactor, and it is possible to artificially increase alkalinity by dosing chemicals to the anaerobic reactor. Such artificial reduction in the ratio may hide the inefficient working of methanogenic consortia. While this ratio is certainly helpful, one must pay attention to the numerator value of this ratio, since it gives an approximate concentration of volatile fatty acids accumulating in an anaerobic reactor. Hence, if the numerator of Ripley's ratio has a higher than normal value, a thorough analysis of the process must be performed. Well, that concludes today's video. I hope this video gave you a thorough background on the concept of using volatile fatty acids as an indicator of anaerobic digestion health. If you have any further questions in this regard, please feel free to contact us at the contact details given below. Thank you so much for your time and attention, and I look forward to seeing you in the next lecture of this video series. Thanks and bye.